So our next speaker is Dr. Ganesh Subramanian, who is a professor at Engineering Mechanics Unit at JNCSR Bangalore. His research focuses on microhydrodynamics, active matter, hydrodynamic stability, particle motion in stratified fluids, and complex fluids. So I request Professor Subramanian to please start the talk.
Yeah, thank you for the invitation. I was hoping I would have a 10 minutes break to just sort out Zoom thing, but can all of you see the presentation?
Yeah, it's visible.
Yes, Professor, it is visible.
Okay. And if I scroll through, you can see the other slides also. Right?
Yeah.
Okay. I'm very happy to be a part of this symposium in honor of Bala. And I don't know how much Bala remembers, but Bala and I had our original interaction almost 20 years back in 2002, I think, when I was giving what was supposed to be a job talk in IISc. And I think he was in the audience and he surprised me or cornered me with a question on the Safman lift force or something along those lines. And so we have occasionally been in touch. And I think I also spoke to him about JNCSR in 2005 before taking a decision to join the center. So it's good to be giving a talk in his honor. So unlike the earlier talks today, this talk is not is on a topic that I can't claim to have been directly involved in, although I've been witness to the progress in it, having worked for John Brady, who has been working on this had been working on this topic actively. So it's more along pedagogical lines. And the idea, as the topic suggests, is to just comment on the rheology of a dilute suspension of particles. Okay? So this is what I had in mind. So I originally wanted to talk about suspensions of both spherical and non-spherical particles. But then as I worked on the slides, I thought I'll barely have time to cover spherical particles, at least if I want to make a few points clear. So the idea I wanted to focus on is known as the rheological indeterminacy problem that enters the dilute suspension rheology calculation, and we'll get to that. But in simple terms, what we want to know is the properties of a suspension, the rheological properties of a suspension in an imposed linear flow. And a canonical example of such a flow is simple shear flow. It's the only linear flow with straight streamlines. And the velocity profile is here. So you have 1 being the flow direction, 2 being the gradient direction, and 3 being the vorticity. And you can see U1 is proportional to the gradient coordinate, with the constant of proportionality being the velocity gradient, a characteristic scale for the velocity gradient. So this is the shear rate, gamma dot, and the inverse shear rate serves as a useful measure for the flow time scale. Okay. And so I just have a slide on the applications of suspensions. You know, there are very many applications. In fact, this slide focuses more on suspensions of anisotropic particles, but you have applications ranging from biological fluids at the micron level to problems involving cloud radiation forcing, which has implications for the Earth atmosphere radiation budget. So, you have clouds in climate, biology, chemical engineering, wastewater treatment tanks, volcanic eruptions, which are geological flows, and so on. So it is a problem of enormous importance. Okay? And so the question that I'll try to address is simple. What is the viscosity of a suspension as a function of the shear rate, if one were to go to try and calculate this? Okay. And suspensions are non-newtonian fluids in general. And so the shear viscosity doesn't alone characterize its property, at least in viscometric flows like simple shear. So there are 2 other properties that come in, rheological properties, and they are the normal stress differences, the first and the second normal stress difference. So the first normal stress difference is the difference between the diagonal components of the stress tensor, the one along the flow minus the one along the gradient. Okay? So if this is denoted as N1, and then you have the second normal stress difference, which is N2, which is the difference between the principal components along the gradient and vorticity directions, 2 and 3. Okay? And so N1 and N2 are, like I said, signatures of non-Newtonian behavior. And these figures highlight what they can do in canonical situations. So N1, when positive, leads to what's known as the rod climbing effect. And this polymer solutions exhibit this very readily at high concentrations. Okay? So instead of a Newtonian fluid dipping in the vicinity of a rotating rod, on account of an elastic hoop stress, the polymer actually rises up the rod. Okay? And the second normal stress difference is more subtle, at least for polymeric solutions, because polymer solutions have N2s much smaller than N1. Okay? Even at high concentrations, N2 is about 10 to 30% of N1. Okay? But you can see its effect, and one of its effects is flow along a tilted trough where the free surface bumps up if N2 is negative. Okay? Another N2 related effect is the existence of a transverse circulation in a pressure driven flow through a duct of a non-circular cross section. Okay? So these are examples of various cross sections leading to flows of different symmetries. Okay? So in general, N1 can be thought of as a tension along streamlines, while at least when N1 is greater than 0, and when N2 is less than 0, these being the signs typical of polymer solutions, N2 less than 0 corresponds to a tension along vortex lines. Okay, so in fact, in cases where N1 and N2 are comparable, and sometimes N2 is larger, as is the case with suspensions, Stokesian suspensions, you can have a competition with N2 wanting to exhibit a rod dipping effect versus N1 driving a rod climbing effect. Okay? There can also be situations where you can have competing torques on a sedimenting anisotropic particle. But anyway, so this is the underlying expression for the stress. Okay, so I don't want you to pay close attention. I'm not going to be talking about this in any detail. It's just to point out the various terms that contribute to the stress. Okay, so the first term here is the so-called stresslet, which is the symmetric first moment of the surface force density on the particle. Okay, the second is the Brownian stress. That is the entropic penalty that you pay on account of an imposed shear altering the configuration of the particles when there are thermal forces wanting to randomize the underlying configuration. Okay? And then when the particles become large enough or the fluid viscosity becomes small enough, there are additional inertial terms, which one of which, as you can see, has the familiar Reynolds stress form. So these come into play when suspension inertia is important at the microscale. Okay? So I'm not going to be delving into these. So we'll be dealing with Stokesian suspensions here, where you have only these two contributions, the stresslet, which is also termed the hydrodynamic stress, okay, or the viscous stress, and the Brownian stress that has an elastic nature. Okay? And the ratio of these two, you have the stress, hydrodynamic stress scaling viscously, the Brownian stress scaling with KT, and the ratio of the stress is the Peclet number here. And so the stress for a Stokesian suspension is really a function of the concentration of the particles and the Peclet number. Okay? So just to briefly put things in perspective before we narrow our focus onto Stokesian suspensions, you can sort of organize this behavior along Reynolds, Stokes, and Peclet axis, where Reynolds is a measure of fluid inertia. For instance, bubbly flows would have all their inertia in the fluid. Granular flows would have all their inertia in the particles. Okay? And Stokesian suspensions have no inertia, but instead have competition between shear and Brownian motion. Okay? So like I said, when you have Stokesian suspensions, the suspension stress is only a sum of the stresslet and the Brownian stress, okay? The viscous and the thermodynamic elastic stress. And therefore, the rheology is a function of the volume fraction and the Peclet number. Okay, and as you can see, the Peclet number is defined here. Okay, you can interpret it in various ways. We'll be doing that. But it's you can see it's a measure of the ratio of the viscous stress, which is mu gamma dot, to the osmotic pressure scale, which is KT by AQ. And if we are going to talk about dilute suspensions, which is the limit that I'm going to be focusing on, then the relevant volume fraction is going to be small. So if we have spherical particles, it's the usual volume fraction. If you have non-spherical particles, it's the so-called hydrodynamic volume fraction, which is dictated by the largest dimension of the particle. Okay? But in any case, if they are small enough, then the rheology really, you can talk about an expansion in the volume fraction. And at each order in the volume fraction, you can talk about the rheology only as a function of Peclet. Okay? So Stokesian suspensions and spherical particles is the only case that I'm going to be talking about. So the first calculation of the suspension viscosity goes back to Einstein, who determined the suspension viscosity in the complete absence of interactions. Okay, that's the infinitely dilute limit, where each sphere finds itself alone in an unbounded ambient linear flow. Okay, and many of you would have seen this result for the suspension viscosity, where the suspension viscosity is enhanced above that of the solvent viscosity by an amount that is proportional to the volume fraction. And that's understandable because each particle contributes independently. So the effect is additive in terms of the number of particles. And phi halves is appropriately known as the Einstein coefficient. Okay. Now, Einstein did this using a dissipation approach. Okay. But he also didn't consider Brownian motion. Okay. So this phi halves phi is really only the hydrodynamic contribution to the viscosity, which comes, as I said earlier, from the stress-led term in the total suspension stress. Okay. And you could ask, what about Brownian motion? Turns out, at least in the absence of interactions and inertia, Brownian motion has no effect. The stress here for an infinitely dilute suspension in the absence of interactions is entirely hydrodynamic. And that's because we're talking about an ambient linear flow. Now, Brownian motion can either be translational or rotational. So if the Brownian motion, if you're talking about translational Brownian motion, a change in the position of a particle due to Brownian motion doesn't really alter its stresslet because we are limiting ourselves to a linear flow, and the velocity gradient sampled during translational Brownian motion is the same. Okay, and rotational Brownian motion has no effect because the orientation distribution remains isotropic for a sphere in the presence of a shear. It's just that the flow continues to rotate it at a mean value which is equal to the ambient vorticity, okay, or half the ambient vorticity. But the distribution still remains isotropic, so there's no entropic penalty to be paid. And therefore, the Brownian stress is identically zero. And in fact, this expression for the viscosity is valid for any Peclet. Okay, it doesn't matter if the spheres are Brownian or non-Brownian. It's valid for any ambient linear flow. So the viscosity is just a constant independent of flow type. And therefore, a dilute suspension, an infinitely dilute suspension of spheres, behaves as a Newtonian fluid with an enhanced viscosity. Okay. Now, the Brownian stress being identically zero can be seen if you know that the Brownian stress involves the log of the configuration probability. And in the single sphere limit, the configuration probability is just trivially the number density, which is a constant. Okay. So the interesting thing happens when you go to the next order, that is the two-sphere problem. Okay. And this was first investigated in some detail by George Batchelor. Okay, so as indicated in this picture, we are talking about adding up the spheres are now seeing each other, but seeing each other in a pairwise sense. So in any realization, there are only two spheres immersed in an unbounded ambient flow, and we are going to have to calculate the probability distribution of the pair sphere configuration. And the energy dissipated by that configuration if we want to calculate the viscosity. So there are many important differences that make the two-sphere problem actually a much harder problem to solve than the single-sphere problem, especially at large Peclet number. Okay. So the first thing, as implicit in my earlier statement, is that the stress is now a function of Peclet, unlike the single-sphere limit. Okay. So if we want to formulate it in the sense of the Einstein viscosity expression, we are really wanting to calculate the next expression in a power series expansion for the suspension volume fraction. Okay, so we have phi halves at order phi. What is it at order phi squared? Okay, and as I indicated, this is not a number anymore. It is a function of Peclet. So it really depends on whether the shear is weak or strong compared to the restoring effects of Brownian motion. Okay. Now, if it's a function of Peclet, but one might expect that it approaches limiting values in certain asymptotic limits, for instance, in the limit of infinitely weak shear or infinitely strong shear. And we'll consider these limits in turn. Okay. So again, going back to the Stokesian expression for the suspension stress, we have these two terms. We have the hydrodynamic stress. Okay. Now we have the Brownian stress. And unlike the single sphere problem, the Brownian stress is not zero because the pair configuration probability is no longer trivially a constant. It is a non-trivial function of R. Okay. So different pairs don't occur with the same probability. And this is just a sketch of a pair of spheres in an imposed simple shear flow. Okay. Now, this is the expression for the stress. But what I want you to focus on is that it's divided into two parts, a part that scales with the number density or volume fraction. That's the part that I've already discussed. That's the single sphere contribution. Okay, that was calculated by Einstein. Okay, and there are two parts that scale with n squared or phi squared, really, since phi is proportional to n. One is in the hydrodynamic stress, and you can see that this involves an S prime rather than an S, and that's because it's the correction to the single sphere stresslet. Okay, that determines the hydrodynamic stress to order phi squared. And then there is a non-trivial Brownian stress, like I already indicated. Okay. Now, the key quantity here, which is the pair distribution function. This is really characterizes the configuration probability of a pair of spheres which are separated by a vector R, as indicated in this figure. So we can ask for the probability that a second sphere is at a position R relative to the first sphere, which is at the origin, okay, in an ambient linear flow, in this case, that being simple shear. So it's the normalized pair probability. Okay, so given the first sphere, the probability of a second sphere is the number density times G. So for infinitely far large separations, G would approach 1, indicating a lack of correlation. Now, G, the pair distribution function, satisfies a convection-diffusion equation in the pair space, which is the two-body Smolakowski equation. Okay. There is a relative convection term that involves the difference between the two sphere velocities, and then a diffusion term. And you can see that Peclet number appropriately measures the relative importance of convection as vis-a-vis diffusion. Okay. Now, these are in general very complicated functions of R because you are including hydrodynamic interactions. But the most important part here is that the particle velocity field, okay, or the relative trajectories of the two spheres is governed by U2 minus U1. That is a compressible flow. So though the underlying fluid flow is incompressible, the particle velocity field due to hydrodynamic interactions has a non-trivial divergence. Okay, and this is crucial to the development of a non-trivial pair probability. Now, I had told you about the correction to the stresslet. Now, there are reasons why this calculation took a long time. If you actually do the magnitude of the stresslet correction, then you will realize that a far field second sphere perturbs the stresslet of a given first sphere by an amount which is proportional to 1 by r cube. So S prime here is really proportional to 1 by r cube because the velocity disturbance is 1 by r squared. The stresslet scales as the velocity gradient, which is 1 by r cube. And then to calculate S prime, you have to add up 1 by r cubed over an infinite three-dimensional volume. And that integral is not really well defined. Okay, so there is a renormalization involved here, which was first correctly done by Batchelor and others in the 1970s. Okay, so now the effect of Brownian motion, which comes in at the two sphere level, is in two ways. One is a direct contribution via the Brownian stress. So this stress scales as kT. Okay, and because it scales as kT, like we discussed, its ratio to the viscous stress, which is the stresslet, is 1 by Peclet. So you expect the Brownian stress to be dominant for small Peclet, whereas the hydrodynamic stress would be dominant for large Peclet. Okay? But importantly, Brownian motion continues to play a role at large Peclet, and that is via the pair distribution function, because as we'll see, there are problems associated with the pair distribution function at large Peclet, owing to which Brownian motion can continue to play a crucial role at large Peclet. Okay. So we'll first look at the small Peclet limit, okay, which you could say is the near equilibrium scenario because we are talking about a weak shear distorting the equilibrium state of a colloidal fluid, colloidal suspension. So in this case, we expect the microstructure to be nearly isotropic because the perturbation due to shear is weak. Okay. And one can expect the pair distribution function, which is the key quantity that's to be calculated. It can be expanded about the uncorrelated state, which for a dilute suspension is just 1. Okay. And you can expand it in powers of Peclet. And now here, Peclet, as we have already seen, is this. Okay. Now I can rewrite this also as the ratio of 2 timescales. Okay. This is a squared by d by the flow timescale, which is the inverse of the shear rate. Okay. Now a squared by d is the characteristic restoring timescale due to Brownian diffusion. Okay, so if I distort the suspension, it's going to return to equilibrium in a time scale of order a squared by d due to rapid diffusion of the underlying particles. Okay, so really, Peclet tells you the ratio of the restoring or intrinsic time scale, microstructural time scale, to the imposed or extrinsic time scale. Okay, so in the limit of large Peclet, you have the microstructural relaxation time being much smaller than the imposed flow time. Okay? And in this limit of a slow flow, one actually, there are, based on general considerations, one expects the rheology to be governed by a so-called retarded motion expansion. Now, this terminology comes from the polymeric fluid scenario, where Peclet is replaced by Deborah. Okay? Now, Deborah number is the ratio of the intrinsic entropic relaxation timescale of a polymer to the imposed flow timescale. And for small Deborah, the stress for a polymeric fluid can be expanded in, loosely speaking, powers of the velocity gradient. Okay, with each successive terms in this successive term in this expansion being smaller than the preceding one by a Deborah number. So you have the Newtonian fluid at leading order. At the second order, you have appropriately perhaps the second order fluid, which contains the first non-Newtonian signatures of normal stress differences. Then you have the third order fluid where you have the first effects of the shear thinning of the viscosity. Then at fourth order, you have shear thinning of the normal stress coefficients and so on. Okay. So for small Peclet, one would, so the important thing about the retarded motion expansion is that it is restricted in its limit, that it's only valid for slow and slowly varying flows, but it has a universal validity in that almost all polymeric constitutive equations reduce to the retarded motion expansion when you take the limit of a weak flow. Okay. So now one expects for a Stokesian suspension, okay, where, as we argue, the intrinsic timescale is much smaller than the extrinsic flow imposed one. Therefore, Peclet will play the role of Deborah, and one can expect a retarded motion expansion similar to this, except that I replace Deborah by Peclet. Okay. And that Peclet comes from the expansion of the pair distribution function. So based on this consideration, one would expect a leading order viscosity. So remember, we are talking about the pair level. So we are talking about a phi squared viscosity leading order, normal stress differences at phi squared Peclet, shear thinning at phi squared Peclet squared, and so on. Okay. And
Professor Subramanian, can I request you to finish the talk in a few minutes so that we have time for question answer? In a few minutes, yes.
Yeah, okay. So the idea is that the small Peclet rheology plays out in an expected manner, except that at the Stokesian suspensions turns out to be more complicated. Okay, the regular expansion of G breaks down beyond a certain order. Okay, and as a result, you have the retarded motion expansion not being of universal applicability, unlike the polymeric case. Okay, but what does hold true is that you obtain a order phi squared Newtonian viscosity, and you obtain N1 and N2 as given here. This was first calculated by John Brady in the mid-90s. N1 is positive, N2 is negative for small Peclet. Okay, but you have the normal stress differences being comparable in magnitude, unlike the polymeric case. Okay. Now comes the large Peclet case. Okay, and if you remember, G satisfied the Smolakowski equation, which had both convective and diffusive terms. Okay. Now, when you naively take the limit, naively perhaps take the limit of infinite Peclet, you can push out the diffusion term, and you just have a convection term, and then G is just convected along pair trajectories, and that leads to the immediate conclusion that the topology of pair trajectories is crucial to rheology. Okay, and this can be seen by two examples. Okay, there are ambient flows like planar extension, where all the paired trajectories are open, but there are also ambient flows like simple shear, where the subset of paired trajectories is closed. Okay, and in fact, the simple shear is not the only flow. There, in the one parameter family of planar linear flows, there exists a range of hyperbolic linear flows which also have closed trajectories. Now, why is this important? I can write the pair distribution function for large Peclet in this form, okay, where C1 and C2 are the trajectory labels, okay, and G naught of R is the isotropic isotropic function of separation, okay. So for flows which lead to open trajectories, we have an isotropic function. Remarkably, though the path lines are very anisotropic, the pair distribution function remains isotropic. Whereas for closed trajectory flows, you have this amplitude function being indeterminate. In other words, it's not unique. You can have A being an arbitrary function of C1 and C2, that's an allowed solution. And therefore, you have an infinite number of solutions for the pair distribution in the limit Peclet equals infinity, all of which are plausible microstructures, okay, and all of which leads to different answers for the rheological properties. And this is what leads to a rheological indeterminacy. This occurs in other problems too, but this certainly occurs in this problem. And therefore, one is faced with the problem that one can't solve for the viscosity in ambient flows that lead to closed pair trajectories. Okay. Now, for the open trajectories, the calculation is fairly straightforward, and I indicate the result here. The zero Peclet viscosity you already saw here. This is the infinite Peclet viscosity by solving for the convective evolution of the pair distribution. And the implication is that there is a mild thickening at order phi squared, which is consistent with intuition. Okay. But for closed trajectories, you don't know this coefficient, at least not in the straightforward manner where you take Peclet to infinity. Okay. Now, what I'm going to end it in a couple of minutes. These are just ways to resolve this indeterminacy. And you can start with a pure hydrodynamic limit where there are no interparticle forces. And the resolution lies in recognizing that weak Brownian motion plays a singular role. Okay. And the order of the limits is important. So in what I sketched here, the question mark here in the viscosity expression arises because I take the limit of infinite Peclet first and the limit of infinite time later. And the order of the limits is important. So I have to take the limit of infinite time before the limit of infinite Peclet. Okay. And this is because I allow for weak Brownian motion to act over an infinite time to set up a unique steady state before I take the limit of infinite Peclet. And if this is done, then you have a unique solution for this amplitude. Okay. And Brownian motion will indeed lead to a unique steady state. Okay. Now, the G, the pair distribution function, importantly, will not be isotropic. And this is important. That means that if I consider the order phi problem and the order phi squared problem, there are differences. The order phi problem, as we already saw, leads to a Newtonian rheology. Okay. The order phi squared problem, you could say, leads to a restricted Newtonian rheology because it leads to a viscosity that is independent of flow type, as is required for a Newtonian fluid, only for ambient flows that lead to open trajectories. In general, it's going to be a function of flow type if the ambient flow contains closed trajectories. Okay. But the closed trajectory calculation has never been done. It's very, very involved algebraically. But more importantly, it's never been done because of this reason. Okay, so this is a figure from Bachelor's original paper, where this is the sphere, excluded volume sphere of radius 2a. And that there practically coincident with it is the separatrix, which corresponds to the label R2 squared by A squared equals 0. The minimum separation of the separatrix is 4 into 10 power minus 5a. Okay, so it's almost 10 power minus 5 times the particle radius. And this is just extraordinarily small. It will be smaller for the other ambient linear flows. And this is typically certainly smaller than typical roughness elements on particles. And therefore, the interaction of rough particles departs from the theoretical scenario of smooth particles. Okay? So though the smooth particle scenario is important, theoretically speaking, in practice, there are short-range interactions which will completely overwhelm any effects of the separatrix. And I'm just showing you a series of plots obtained from a two-body theory, which includes short-range repulsive interactions. And you can sort of see the short-range repulsive interaction is parameterized by the ratio B by A. Okay, so if B by A equals 1, there is no repulsion, but B by A being just greater than 1 corresponds to a very short range repulsion. And you can see that these circles are the total viscosity. The total viscosity starts from a small shear plateau, shear thins. So there is initial shear thinning, but eventually there is shear thickening. Okay, and this shear thickening is because of lubrication stresses arising from closely separated particles. And the general tendency of a suspension, therefore, is that the viscosity starts from a small shear plateau, shear thins, and followed by shear thickening at larger Peclet. And this shear thickening, because it arises from lubrication, has given rise to what is known as hydrocluster interpretation. So you can see in these cartoons, the way of thinking about the shear thickening is that there are larger and larger clusters of particles held together by these short-range lubrication interactions, okay, which eventually lead to a rise in the viscosity. Okay. Now, until about maybe a few years back, the lubrication-induced shear thickening was believed to be the underlying mechanism for shear thickening and suspensions. But I must mention that at larger volume fractions, the shear thickening mechanism seems to shift from hydrodynamics to direct frictional contact. And that leads to almost, in fact, this curve is more representative of the shear thickening that arises from discontinuous frictional contacts, which leads to almost a discontinuous rise in the viscosity. Okay. So this is a table summarizing the properties of the small Peclet and large Peclet Stokesian suspension rheology. I won't go through this, but I just want to end with this slide. This is the last slide, saying that because the closed trajectory topology that you obtain in the purely hydrodynamic limit is structurally unstable from the dynamical perspective, it's not only Brownian motion, but a number of other physical effects, which even if weak in magnitude, can lead to significant and non-trivial rheological signatures. And I've just included a few of them, all of which are capable and have been shown either via computations or theory to pronouncedly alter the original closed trajectory topology, whether it be deviation from rigid particles, effects of inertia, or going away from the spherical geometry. So with that, I'll be happy to answer any questions if there is still time. Thank you.
Thank you, Professor Subramanian. We can take just one quick question and then we can move to the next topic. No question. All right. Thanks again, Professor Subramanian, for the interesting talk.